Hi, Algebra 2 Honor students. This is Unit 14, Day 7. Today we're looking at the graphs of the reciprocal trig functions. So at this point, hopefully you're feeling pretty confident about sine and cosine and some of their transformations. And we've graphed tangent a little bit. We're going to revisit what that graph looks like today. But our main focus is to now think about, well, what does the graph of cosecant look like? So if you have some graph paper, we're going to set up cosecant by remembering that cosecant is the reciprocal of sine. So it is 1 over sine of x. And I think for that reason, if we're finding reciprocal values, let's go ahead and graph what sine x looks like over one cycle from 0 to 2 pi. And then we're going to think about if I take the y values on that graph and find their reciprocals, that's going to give me an indication as to what the graph of cosecant looks like. So let's go ahead and set that up. Okay. So I'm going to make every 2 spaces 1 unit just to kind of space myself out a little bit here. So we'll set the y values to be the following there. And then to space this out a little bit on the x-axis as well, let's make every 3 spaces pi over 2. So there's pi over 2, this is pi, 3 pi over 2, and then 1, 2, 3. That would be 2 pi right there. Okay. So if I want to graph just sine x first, since that's not the actual graph that we're looking at, I'm going to graph it as a dotted line. Okay, so sine has these 5 key points for one cycle of its domain from 0 to 2 pi. So there, as a dotted curve, is what sine x looks like. And we're going to base our graph of cosecant off of that. So let's think about some key points here, like the fact that at a y value of 1 on the sine curve, 1 over 1 is still 1 for the graph of cosecant. So this point will stay exactly the same when we graph cosecant. Same thing for negative 1. If we have 1 over negative 1, that's still going to be a point at negative 1 for the graph of cosecant. So these over the domain from 0 to 2 pi, those are the only 2 points that actually are the same. Everything else looks different. So let's think about some of the other ideas here then. The other key points that I graph for the sine curve are at 0. Well, what's 1 over 0? 1 over 0 is undefined. And graphically what we see when a function is undefined like that is we're going to see vertical asymptotes, which we haven't graphed in a little while, but here they are. So we've got vertical asymptotes wherever sine equals 0. That makes sense. 1 over 0 is undefined. So we have 0, pi, and 2 pi. And then what's happening everywhere else? All right, well, at a certain point, we would get on the sine curve a y value of 1/2. So what happens when I flip 1/2? Doesn't it become y equals 2? In fact, the closer I get to these zeros, the y values on sine are getting smaller and smaller and smaller, like 1/3, 1/4, 1/5, 1/6. Think about flipping those over. It's going to become 2, 3, 4, 5, 6. They're getting really tiny. So the smaller sine gets, the closer it gets to 0, cosecant's going to get pretty large near the ends. And that's what we see anyway when graphs approach asymptotes like this. So you're going to get sort of a parabola shape from 0 to pi. And then for that same reason, on the negative side, if you have a y value of -1/2 or -1/3 or -1/4, it's going to become -2, -3, -4. The closer sine gets to 0, cosecant's going to start going down forever and approach -infinity there. Okay. So that's exactly what the graph of cosecant looks like. That is one cycle of the cosecant graph from 0 to 2 pi. So it's definitely a little bit weird looking. You know, if we think about the domain and the range of this graph, the domain is weird. It's everything, all real numbers, and that's the symbol for all real numbers, except I don't want 0, I don't want pi, I don't want 2 pi. And by the way, this graph would keep going on forever and ever. It would have an asymptote at 3 pi and 4 pi and 5 pi and so on. So what I'm going to write is that I don't want pi n, where n is an element of the integers. That funny looking z is the set of all integers. So that's the most concise way of writing domain. Everything except pi times n, where n can be any integer. And that looks a little scary, but we'll talk about that more in class. Ranges should be a little bit easier for us. The range would be -infinity to stop there at -1 for cosecant. And then notice how this entire block of sine is not included in the range, but then it picks up again from 1 to infinity. So that's the range of the graph of cosecant. So I just want to introduce you to that a little bit. That may not be a huge focus in the unit, but just thinking about domain and range for these graphs that start having some crazy looking asymptotes here. All right, let's move on to talk about secant then. Secant of x is going to equal 1 over cosine x. So let's see what we get here. We're going to approach it from really the same exact perspective. Let's sketch one cycle of cosine x. We'll do it as kind of a dotted curve. And then after we sketch that one cycle of cos, we'll think about the reciprocal values and how that generates the graph of secant. So here's 1, here's -1. The scale that I used up above was every 3 spaces was pi over 2. We'll try and keep that consistent. Okay, and then let's plot the 5 key points that we need for the cosine curve. So cosine starts at 1, 0, -1, 0, +1. So here is one cycle of cos. Okay. Let's talk about what happens for the graph of secant, where cosine is 1. 1 over 1 is still 1. So just like we saw for up above, these points are definitely points on cosecant. Where cosine is -1, secant is also -1. So this point will hold true as well. What's going to happen where cosine equals 0? If this denominator is 0, 1 over 0, undefined. Okay, so we got some vertical asymptotes going on, just like we had up above. And then same idea. As cosine approaches 0, secant's heading to infinity. As the denominator gets really, really small here, 1 over that number is getting really large. So we're going to see this part of the graph from 0 to pi over 2. In between pi over 2 and 3 pi over 2, we've got that upside down parabola piece. I'm going to work backwards here from 2 pi to 3 pi over 2. As cosine decreases working backwards, this graph's going to head up to infinity. And the phrase that I like to think of, I'm just kind of looking at the way the graph looks, is I kind of think secant is sad, don't you? It looks like some crying eyes. So if you're just graphing secant from 0 to 2 pi, if you're a memorizer of some sort, then maybe remembering that secant is sad is a good quick reference point. Say, oh yeah, I kind of remember what that one looks like now. Okay, but that is the graph of secant. We've got one more to go. We've got to graph tan. And when I graph tan, I'm going to graph it separate from cotangent because the two of them on the same set of axes wind up having a lot of overlap there. So I want to make sure that I can kind of separate the two so I know which one's which. So for the graph of tan, let's set up some very similar axes here. So we'll set the scale on the y-axis the same. I'll do my x-axis scale the same. Let's see, can I squeeze all this in here? I think we can make it happen. All right, pi over 2, pi, 3 pi over 2. So if you look back at our example with tan, the way you graph tan is you think of it as sine over cos, right? So if you do sine divided by cosine, wherever cosine is 0, that's going to be an issue for tan. You're going to have asymptotes at pi over 2 and 3 pi over 2, kind of just like secant up above. And wherever sine equals 0, tangent equals 0. So that's in these 3 locations. Tan, if you remember, looks like this. Has this kind of S-type curve in the middle. And it would repeat that pattern forever and ever. It would keep going in that same repeated pattern. But that's what the graph of tan looks like. So then I have to think about, all right, well, cotangent, it's reciprocal. You can think of it as 1 over tan, or if you even wanted to, you could do cos over sine. That would be a way to generate the graph as well. Let's see if I can fit all this in here. All right, 1, -1. Did I give myself enough space? Pi, just barely, but we can do it. All right, so if I make every 3 spaces another pi over 2, that's going to just about fit. Okay, let's talk about where tan is 0. Where tan is 0, because if this is 1 over tan, right? That's going to be an issue for cotangent. If tan is equal to 0, cotangent has asymptotes at 0, at pi, and all the way down here at 2 pi. Okay, here's what's weird though. Where tan has an asymptote, cotangent winds up being 0. Think of it this way. Where tan has an asymptote, that came from 1 over 0. Well, for cotangent, that gets flipped over. 0 over 1 is now 0 again. So that looks a little bit weird, right? Okay, let's kind of work our way backwards here. When tan gets really, really small and close to 0, the reciprocals are getting bigger and bigger and bigger and bigger. So what's going to happen is it's going to approach that vertical asymptote and get really, really tall as I get close to 0 here. But then once I go through pi over 2, it's going to head on down towards this vertical asymptote because now we're in negative land, right? Okay, so this part of the graph is negative. As we get closer to 0, even though that's getting really, really small, cotangent's going to get really, really largely negative. And the nice thing about cotangent is it then just repeats that pattern forever and ever and ever. So repeat that same exact cycle from pi to 2 pi. And in between 2 pi and 3 pi, same thing. If I went over here and went out to negative pi, I would see that same exact thing graphed. Okay. So here's what the graph of cotangent looks like. And when we get back to class, maybe I'll even show you that if you set your axes correctly on your calculator, you can graph these just like I'm seeing them right now. 1 over tan, 1 over cos, 1 over sine. If you type those into y equals, you're going to see these graphs if you set your window and your domains correctly. Okay. All right, that's a pretty big derivation here for the reciprocal graphs. What we're going to do is maybe just take a little bit more of a look into changing these ever so slightly in terms of some transformations. So let's try these. So if I look at something like cosecant of 2x, and we'll graph this from 0 to 2 pi. For cosecant of 2x, we're increasing the frequency. Okay. So when I graphed cosecant a minute ago, cosecant looked like this. Parabola, upside down parabola. That was one cycle of cosecant. Well, here's the deal. If it's cosecant of 2x, the period of cosecant is 2 pi. So 2 pi divided by the new frequency gives you a period of pi. You're going to have to see this completed by the time you get to pi. So if I'm graphing this to 2 pi, I'm going to see this whole thing repeated again. So that's kind of weird. All right, so here we go. So if we set our axes, give myself a lot of space here. If we set our axes kind of the same way that maybe we did on the front. So here's 1 to negative 1. You know what, this time, let me think about what makes sense. We could probably still go every 3 spaces. It's probably not a big deal. So there's pi over 2, pi, 3 pi over 2, and then 2 pi. Okay. What we said is we have to see that whole cosecant graph completed by pi. So if I'm going to see an asymptote here, I'm also going to see an asymptote at pi over 2. And there would also be one at 0. So this first cycle of cosecant, this is what it's going to look like. You're going to see the smiling parabola touch at 1. And that place where it hits the lowest value of 1 up here is midway in between 0 and pi over 2. So similarly, midway in between pi over 2 and pi, we're going to be at negative 1. Okay, and then you're going to see the upside down parabola. So that's the first part. But if I am graphing it all the way to 2 pi, I now want to go ahead and extend this and just repeat it one more time. Asymptote at 3 pi over 2, another asymptote at 2 pi. So we're just going to see the same pattern repeat itself to get one more cycle graphed in there. Okay, so that's what cosecant of 2x will look like, 2 cycles by 2 pi. You can see how we increase the number of asymptotes because of that. Okay, so it takes a little while to get used to, but let's maybe just try one more of these. So we'll try one with secant. So we're going to do not a transformation, but I'm going to change the domain that we graph secant over. So secant we graphed earlier from 0 to 2 pi. I want to see, well, what does it look like from negative 2 pi to positive 2 pi? If I extend it out even further to the left than just looking at it at x equals 0. Well, in order to do that, I'm going to shift where I draw my y-axis. I'm usually all the way off to the left here. But if I want to equally spaced for the domain that we're graphing over, it makes sense to put it right straight up and down the middle. Okay, so let's set our axes the same way, set them up. So this is pi over 2, and then we'll do pi, 3 pi over 2, and 2 pi. All right, same thing going the other way. 1, 2, 3, 3. Go a little bit further. Okay, negative 2 pi is all the way out there. All right, I think I've got everything. All right, well, what we can do is we can just work on the right side first, see if we remember what secant looks like. And then after we graph secant, we can always think about, well, how does that get mirrored on the other side of the y-axis? Secant's the one that's sad, and secant has asymptotes at pi over 2 and 3 pi over 2. Okay, wherever cosine was 0, that's where secant had its asymptotes. So let's see, secant looks like this with its crying eyes. It has this point down here, and then it looks like that. Okay. Well, if I think about what happens on the other side, okay, so you'll notice that you get in the asymptotes are pi apart, right? So if I go pi away from here, there's going to be an asymptote at negative pi over 2 and negative 3 pi over 2 and so on, and it would carry on in that fashion. And to continue on with this curve, what we know about cosine and actually secant is it has y-axis symmetry. So it's going to continue and have that parabola shape, and then you're going to see the upside down parabola. And then you would see the right side up parabola, and so on and so forth. So in between the asymptotes, you're going to see the upside down parabola. And now on the other side of this asymptote, you'll see half of the right side up parabola. If I had gone all the way to negative 5 pi over 2, where that next asymptote occurs, it would have that same pattern over here as well. Okay, but all I should see from negative 2 pi to positive 2 pi are these, I guess, 3 completed parabola type shapes, and then these sort of crying eyes on the outside. Okay. So just a little bit of a taste as to what the reciprocal graphs look like, maybe over different domains, some slight transformations, but if you think we're heading here with some of the transformations we've done with sine and cos, we're not quite going to go that in depth with it. Maybe just some slight transformations. Okay, so we'll do some more practice with that next time we're in class. But that is it for today's lesson on reciprocal graphs. More practice to come. Have a great rest of your day.